Hello and welcome to Precision Stuff. Today we'll be talking about transient thermal diffusion. This is a topic that's come up recently in a few different situations, both battery related and precision machine design, and it's a very useful piece of analysis to have in your toolkit. Solves a lot of problems. The first issue was battery thermal runaway. Let's say you have a battery, it has an enclosure, battery inside has a bad day, there's some gas and flame, but you want to make your enclosure really light. Let's say it's thin aluminum. Is it going to burn through if it's exposed to a short duration at high temperature? Let's say it's a few seconds at 1000 Celsius going over this sheet. Maybe we want an insulator. How thick does the insulator need to be so that the backside of the insulator is low enough that the aluminum doesn't burn through? So this is like an insulation kind of problem, and you're trying to figure out what amount of material do I need. In precision machine world, let's say you have a giant granite block and you have your linear motor set up on top, moving back and forth. Linear motor makes heat. Essentially, you're going to drive a thermal gradient into the granite. The thermal gradient creates strain, it creates deflection. Your whole granite block is going to be curved. That is unfortunate if you want to make accurate shapes. How long do you need to wait for that temperature gradient to equalize to the point where then you have dimensional stability? So this is how much time does it take to make sure there is no gradient? So this is insulation, and this is like no gradient. You want to make sure it's all the same. Normally, your thermal tools would actually not be that useful here. So if you start with a lumped parameter model, let's say you have like your enclosure and you have an insulator in front of it, and if you start trying to write R's and C's and time constants and heat capacities to make a lumped model for this, you're going to get the answer wrong because it's not you can't lump it because we're looking at really sharp temperature distributions in the material. This will capture average temperature only. So if you wanted to use these kind of techniques, you got to chop it up into a ton of R's and C's, a bunch of little regions that are all connected to each other. And you can do that. You can write a nodal network model. You can write a finite difference equation. You can do FEA. It takes a lot longer. So you're going to be spooling up this huge program. So the way we can solve these problems easily is with transient thermal diffusion. And there's a really critical kind of test solution for this, and that's called the semi-infinite solid. So if I have a infinite plane, and it's infinitely deep in one direction, I have this huge block of material, it goes off to infinity. This is the semi-infinite solid. And it all starts out at t initial. And I can draw a little coordinate system, and I can say I'm x, here's a point that's x below the surface. Then all of a sudden at time t equals 0, I make the temperature suddenly go to t surface. Then the question is, what is the temperature distribution as a function of time and distance in this material? First, you get a really steep temperature curve, and then it will slowly kind of diffuse through the material, and you'll heat it. If you're really good at calculus, you can actually just solve the heat equation and get the answer. I am not that good at calculus, but I do have the answer. Theta of x and t is equal to the complementary error function of the Fourier number. And that's it. Thank you very much for listening to Precision Stuff, and have a good week. Just kidding. What does this mean, and how do we actually use it? We have to break this down to 3 parts. What is theta? Theta is non-dimensional temperature. So in this case, I've defined it as theta of x and t is equal to the temperature of x and t, the time and place we care about, minus t initial. Actually, I'm going to use capital T for temperatures, divided by t surface minus t initial. So theta is the are we there yet function. Like if theta equals 0, you're stuck at initial temperature. If theta equals 1, you've made it your way to the final temperature. If theta equals 0.4, you are 40% of the way from your initial temperature to the final temperature. So the kind of mapping is like this. T initial, t surface, theta equals 0, theta equals 1, and it is a line that looks like that. So this is a non-dimensional temperature because we're going to put a non-dimensional number into an equation. It better pop out a non-dimensional number on the other side. All right, so what is the complementary error function? Well, clearly, complementary error function of x is just 1 minus the error function of x. What more do you need to know? Well, the error function is actually a pretty unholy integral. It's 2 over root pi integral from 0 to z of e to the minus t squared dt evaluated at z. It's challenging, but this is known. This is solved. If you give me I guess x. If you give me x, I can tell you the error function of x. The complementary error function looks kind of like a sigmoidal curve, and we'll use that to our advantage later. So this is a known function. This is not really doing anything interesting. Thermally, this is just relating time and such. So what's going on in the Fourier number? The Fourier number is the meat and potatoes of this whole situation. Fourier number is equal to x over square root of 4 alpha t. This is non-dimensional, and it's a ratio of distances. So x is units of meters. That's how far we are below the surface. So therefore, the bottom better also be units of meters. And what is this? 4 alpha t. Well, 4 is 4. Alpha is diffusivity. So alpha equals k over rho c. And the units are meters squared per second. Kind of weird. You know, it's not a velocity, it's a area per second. That kind of confuses people. What does it mean? Well, something that is very diffusive moves more thermal energy than it stores. So K is thermal conductivity. That's basically how fast you can move heat through the material. And then rho C is density, specific heat capacity. That's how much energy you store. So a nice metal, gold, silver, or copper, lots of conductivity per energy storage. And something like a plastic or a rubber or an insulator is not going to have the same amount of conductivity per energy storage. So now you're thinking, well, great, now I need to calculate alpha, then I need to calculate the Fourier number, like what's going on here, what's the intuition? It turns out there's only 4 things that matter in the world of diffusivity. It's actually quite easy. If you are a shiny electrical metal, if you are silver, gold, copper, aluminum, your diffusivity, alpha, equals 1e minus 4. Within a factor of 2. Like a nice pure silver is twice as high, and a dull aluminum alloy is half as much, but like factor of 2. If you are a dull structural metal, let's talk about steel, let's talk about stainless, Inco, Ti, alpha equals 1e minus 5, plus or minus a factor of 2. High carbon steel is on the high end, and a stainless is on the low end. Okay, if you're a rock, or like sand, or some sort of like brick, dirt basically, alpha equals 1e minus 6, also plus or minus a factor of 2 among friends. And then finally, this is actually the most important one, every single like plastic, rubber, and foam, guess what? Alpha equals 1e minus 7 plus or minus a factor of 2. So there's only really 3 orders of magnitude that describe all of diffusivity for essentially every single material. And you can go calculate it if you know the details, but you can honestly just use this as like a rough lookup table to figure out what you want. So if you know your material, you know your diffusivity, what does the Fourier number really mean? Well, x over square root 4 alpha t. If the Fourier number is large, it means that the spatial distance is longer than the distance that the diffusion wave has traveled. It means you're outside the wave. It means you don't even know that things have started heating up yet. If the Fourier number is really small, it means that the spatial distance is very small relative to the thermal distance, which means you're very much inside the wave. It turns out the only kind of region that matters is 0 to 1 to 2. So the way to think about it is, this is a wave crashing on the shore. If you are at Fourier equals 2, you're standing here and like you can see the wave and maybe your toe is wet, but like not a big deal. If you are at Fourier number equals 1, okay, your shins are wet. But if you're at Fourier number equals 0, you are inside the wave, you are fully wet, maybe your hair is dry. But like this is the kind of understanding you should have for Fourier is, are you inside the wave or are you outside the wave? And this basically tells you either your Fourier number is large and you're insulating, you haven't realized the change in temperature, or it's very, very small and the gradients have equalized. But this is all kind of hand-wavy intuition. How do we use this? Eventually we need to get to a temperature. Well, let's go back to our 2 motivating examples. Let's say I'm trying to answer the question of the battery insulator. So if I want insulation, I'm going to choose Fourier number equals 1. And I want to say, so that means, in this case, x equals square root of 4 alpha t. And I know that I have to survive a 5-second event, and I'm going to use a foam insulator. So how thick does it need to be in order to provide this level of insulation? Well, x equals square root of 4 times 1e minus 7 times 5 seconds. And the answer is about 1.4 millimeters. So already right off the bat, I know that if I have just a little bit over a millimeter of foam, I'm going to be able to do a substantial amount of insulation and protect my thin aluminum enclosure and have low backside temperatures. If I wanted to push Fourier number to 2, you'd end up with like 4 times as much. Okay, now it's like 6 millimeters thick. This is like not a lot of material, and what matters mostly is the thickness and the diffusivity. If I'm looking at a foam and a rubber and they have like similar diffusivities, I'm going to go with the one that's lighter and cheaper so I can make it thicker to get the advantage. Again, they're all about 1e minus 7. Now let's go back to our granite example. I have, granite block, let's say it's 0.1 meters thick. Then the question is, how much time does it take to equalize? In that case, I want to have a low Fourier number. I want to make sure that the top and the bottom are very much the same temperature. I want to be in the wave. So now I'm going to say 0.1 equals 0.1 over 4 alpha. Here I'm going to choose 1e minus 6, and then I'm going to solve for time. So in that case, you arrange this and you get t equals 2,500 seconds. Okay, so this is still all hand-wavy intuition. How do we get to real numbers? So we have to go back to our original equation, which was theta of x and t equals the error function of the Fourier number. Fourier number is doing most of the work, but we need to get all the way out to final answer. So let's actually draw this curve. In the world of theta, the only thing that matters is 0 to 1. In the world of Fourier number, the only thing that matters is 0, 1, and 2. I'm going to draw a dashed line because it turns out that the error function, complementary error function, is basically 1 minus x in this region. And so the actual curve is really close to 1 minus x and starts to diverge a little bit. And there's a few key values that we'll pull out here. So if your Fourier number equals 0, then your error function is going to be 1, and my approximation of 1 minus Fourier number is also going to be 1. If you go to Fourier number equals 0.1, the exact answer is 0.887. My approximation is 0.9. Pretty good. If Fourier number equals 0.5, the exact answer is 0.4795. My approximation is 0.5. Still within a few percent. If you go to Fourier number equals 1, the exact answer is 0.157, which it's basically like 1 over 6. This is where my equation starts to break down. And if you go to 1.5, it starts to drop off really fast. You can see it's kind of tapering off. You get 0.033, and then at 2, you get 0.005. So the moral of the story is, if you are a low Fourier number, you're very much inside the wave, it's basically 1 minus x, you can get arbitrarily close to theta equals 1. Once you get to Fourier number is about 1, you have like a 6x insulation ratio. You've only moved 1/6 of the way of the final temperature. And then here, this would be like a 1 over 30, and then here's like a 1 over 200. Your insulation starts to get really good once you get into the Fourier equals 1 to 2 region. So let's actually back this out to the real math. Let's say my enclosure started out, initial temperature equals 60 Celsius. And let's say for convenience, the final temperature was 1060 Celsius. Well, if my Fourier number equals 1, then theta equals 0.157 equals, t minus 60 over 1,000. This is basically 1/6, so I've gotten my final temperature to about 220 degrees Celsius. And that's fine. Like I can have an aluminum that hits 220 C. It'll lose about half of its strength. It'll still be there. It's not molten. So this is actually a pretty good insulator. Taking the 1,000 Celsius and chopping it down to 220, pretty reasonable. If I made my foam thicker, I could get this to be pretty low. And it doesn't mean that the foam is actually going to survive. It might burn through, it might char, it might do other things, but that's like a material detail. From a conduction standpoint, I'm good to go. Going back to the granite, let's say my T initial was 20 Celsius, and then the surface temperature is going to be 30. And I want to make sure that the top and the bottom of the granite are within 1 Celsius of each other, so 30 and 29. Well, it turns out that basically matches Fourier number of 0.1 because I'm going to get 90% of the way to the final temperature. So that kind of gradient from 30 to 29 is just 1 degree C off, and that corresponds to Fourier number equals 0.1. And if I needed that to be 29.5 or 29.999, I can make the Fourier number smaller and smaller and smaller to get theta arbitrarily close to 1 and make the gradient arbitrarily small. It just takes a lot longer. So this is the kind of use of the semi-infinite solid model to find the answers to transient thermal problems. And this is some good intuition to be built here, but there's a few caveats with what we're doing. It's like, we've been assuming you have an infinitely deep solid that you're then heating from the surface. The two examples I gave were definitely not infinite. They're definitely a finite block, and at some point, the heat will hit the end of the block, and instead of having that curve off to infinity, it's going to be a little bit hotter because you're actually just going to eventually fill up the lumped heat capacity of the block. So if your structure is thin, like maybe 1 Fourier number or below, you're going to be a little bit under predicting when you use this. So the other thing is there's shape and boundary condition also matter here. This is all like kind of planar. If you have a cylinder and you're heating the outside, if you just barely heated the top few microns and you're looking at a really large Fourier number, you're way inside the part, it looks like a semi-infinite solid. But as your Fourier number gets smaller and smaller and smaller, and you are heating in from every single direction, all of a sudden the heat from here and the heat from there, like, wait a minute, I saw you last Thursday. Like, they're all ganging up on a smaller and smaller amount of area. Clearly it took a lot of power to heat up this whole region, and it takes less and less and less. So it's going to take less time to heat the center of that cylinder than a equivalently thick planar solid. The inverse is also true. Let's say you're welding on the inside of a corner. You're applying heat here. Well, the first little bit of material, when you're really high, like if you're looking at this point here, super high Fourier number, the wave hasn't hit you, nothing's going on. But eventually, as you heat more and more and more, as the Fourier number gets smaller, the area keeps getting bigger and bigger and bigger. Actually, it takes more and more power to do that. So the semi-infinite solid model will actually overpredict the temperature because of this curvature. The other thing is that the semi-infinite solid model makes kind of a weird assumption on boundary condition. It assumes that your temperature of your boundary has like suddenly changed from initial to final. And that's pretty difficult to do. It's like a really easy equation, but that's not quite accurate. There are two other boundary conditions you can do. You can do a convection boundary condition. And you can look in the textbook and you can find, theta of x and t equals some function, and is basically still going to have that error function of Fourier times a bunch of other stuff, a bunch of exponentials and details that capture the fact that in the first moment you have hot gas flowing over a cold surface, there's going to be a lot of heat transfer, and then as the surface heats up, actually the heat transfer goes down. It doesn't change the conduction and diffusion inside the material. That's still just what it is. But the actual time versus temperature boundary condition does change when you have a convection situation. The other one that's really useful is a heat flux boundary condition. Let's imagine you're laser welding two sheets of stainless together, and you have a huge high power laser coming in, heating the spot size. What's the time versus temperature through the material? Well, the temperature is really going to get to the melting point, but clearly you're pumping a lot of power in. There's also a version of this equation. It still has the error function of the Fourier number times a bunch of other stuff that now tells you what the temperature versus time is given a certain heat flux. That's also quite useful. So there's a lot of fun applications of this, both in battery and precision. The last one I'll leave you with from an intuition standpoint is if I give you a bar of steel, it's a foot long, and it's an inch in diameter, and I ask you to hold it. That's your hand. And then I pull out a torch, and I start torching the end of it. It's a blue torch, don't worry about it. How long can you hold on? And if you ask this as like an interview question to like a thermal engineer, you're going to get tons of complexity. It's going to be like, well, we have to do the gas combustion to figure out the flame temperature. Then we have to do the flame temperature with like radiation convection over a cylinder to find the tip temperature. And then we have to do a transient nodal network where we do an evolving fin over time to figure out. And the answer is, it doesn't really matter what the temperature at the tip is. Steel diffusivity is so low, it's going to take you 10 minutes to feel anything on this side. And this really freaks people out because it's a really small rod. The heat capacity is low. You think you could really heat it up pretty quickly. The way to think about this is imagine if there's a giant wall of steel and you're on the inside and you put your hand on the inside of the 12-inch thick wall of steel, and someone else has put a torch on the outside, how long can you put your hand against the wall? You can keep it there for a long, long time. And this is also an issue if you're heat treating or welding steel and you have giant weldments. It might take hours to days to slowly preheat or post-heat your material, just because steel doesn't move heat that well. Thank you for listening to Precision Stuff. Have a wonderful day.